So good morning, everyone, and welcome to the second day of the technical program of SIGCOMM'. And I'm Li Chen from Zhongguancun Laboratory, Beijing. And today I'll be chairing this session. So this session is NetMon, and it's about network measurement, monitoring, and the failure localization stuff. And we have 6 exciting papers ahead of us. And so without further ado, I will introduce the first speaker. The first speaker is Chen Shou from Peking University. He is supervised by Professor Guyue Liu. And unfortunately, the first author of this paper won't be able to join us today. He is Yunwei Dai from Southeast University. His research focus on DNS security and network traffic analysis. He is also a contributor to the open source DNS software Unbound. If you have any questions, you can contact Yunwei Dai by email after this talk. So please take it away.
Good morning, everyone. I'm Chen Shou from Peking University. Since the original author of this paper could not attend our conference, I will be giving the presenter on their behalf. I'm also honored to be the first presenter today. Today, I'm excited to introduce DNSLogzip, a new approach for compromising DNS logs with both high speed and high compression ratios. Here's a quick look at what I will be talking about today. Why do we need to collect and store DNS logs? Well, DNS logs capture the queries and responses between clients and servers. They are incredibly useful in a few key areas. First, for statistical analysis, understanding usage patterns and how the DNS infrastructure behaves. Second, the security, detecting threats, supporting malicious domains, and investigating attacks. And third, for compliance, many organizations need to log network activity, and DNS logs help meet those requirements. In large-scale setups like ISPs, DNS logs are usually collected using switch port mirroring and DPDK. Here is how it works. First, the switch mirrors DNS query and response packets to a dedicated port. Then, a TAP device sends these packets to multiple processing threads for load balance. Next, DPDK passes the packets, extracts key fields like domain names and IP addresses, and turns them into structured logs. Finally, these logs are compressed, typically using twice like gzip. Now, let's talk about the problem. One Tier 1 ISP we worked with generates 200 TB of raw DNS logs every day. After gzip compression, that's still 55 TB daily. Over 180 days, that adds up to almost 10 petabytes at $20 per terabyte per month. That means $245,000 every month, just for one node. So it's clear we need better compression. So why not just use gzip or similar twice? Well, general purpose compressors work at the character level, like LZ77. For example, it replaces repeated strings with short back pointers. As shown in the figure, the second ABC is replaced with a pointer to the earlier one. But these twice don't understand log structures. They can take advantage of repeated patterns across lines. So we miss a lot of potential for optimization. What about twice like log reducer, log shrink, or denom? They work well for system logs by extracting templates and replacing them with compact IDs. But DNS logs don't have those templates. They are just structured field values. Plus, these twice can't fully leverage the unique features of DNS data, so they don't have much here either. Next, let's take a look at how DNSLogzip works. There are 3 main types of compression approaches. First, character-based twice like gzip, bzip2, and LZMA that directly compress raw data. Second, domain-specific twice like log reduce, log shrink, and denom, which extract templates before compressing. Then there's DNSLogzip. We also pre-process logs, but unlike others, we don't create extra files. That's important because extra files add overhead. DNSLogzip keeps it simple and works seamlessly with any general-purpose compressors, what we call the compression kernel. The key idea of DNSLogzip is to improve compressibility by transforming and reducing logs. We found that 10% of domains account for 90% of lookups, and their results are often stable. For instance, one domain appeared many times but had only 3 different results. By sorting logs with domain, similar entries are grouped together, making compression much more effective. Here's the refinement. When a domain maps to multiple IPs, the order may vary across entries. By sorting the IPs in each entry, we make more lines identical. As shown in the figure, 2 different looking results become the same after sorting, which helps the compressor replace the entry field and improves efficiency. DNS follows a tree structure, so many domain names share the common suffix like .com or .net. To take advantage of this, we sort by reverse the domain names, putting the suffix first. For example, x.com becomes moc.x. This boosts compression by grouping similar suffixes together and show on the right, making logs more uniform and easier to compress. Sorting logs changes their original log order, which means we lost the line sequence. But since we want lossless compression, we need to have a way to restore the original order when decompressing. To do this, we add a line index header that records the original line numbers, as you see in the figure. During decompression, we use the index values to reorder the sorted logs entries back to their original sequence. This ensures the logs are fully restored, exactly as before. Just like we handle line sorting, DNSLogzip also needs to restore the original order of IP addresses within each log entry. To do this, we use a dedicated address index header that records the original positions of addresses before sorting. To keep index compact, DNSLogzip uses different encoding cases depending on how many IP addresses are in the entry. You can see 3 cases illustrated in the figure. The other key part of DNSLogzip is the reducer, which focuses on shrinking the preprocessed file size. We do this using different encoding for both addresses and the timestamps. First, many IP addresses in a lookup result belong to the same subnet, so we just store the differences between them. Second, for timestamps, when many logs arrive within milliseconds, we only record the time difference from the previous entry. This helps cut down the data size significantly. We use field hiding to shrink logs without losing data. For example, if type is A and the R code is 0, we store only the domain name and skip the others. During decompression, if the first field looks like a domain name, we restore type and the R code to their defaults. This makes each line shorter while keeping full recovery possible. We also use a technique called the field replacement. It's designed for DNS system where certain values, like service addresses, show up again and again. That's especially common within the same DNS zone, where queries often hit the same field servers. To avoid repeating these values, we compare each field with the one from the previous line. If they are the same, we just replace it with a simple marker, like a dash. This small change can significantly reduce the file size without losing any information. RFC 1034 says DNS is a case-intensive, so real logs use mostly numbers and lowercase letters. We encode numbers using just 0 to 9 and A to Z, making data more compressor-friendly. This helps character-based compressors like those using Huffman encoding compress better. Now let's look at how DNSLogzip performs in real scenarios. We evaluated DNSLogzip on 3 main metrics: compression ratio, compression speed, and decompression speed. We compared it with popular general-purpose compressors like gzip, bzip2, and LZMA, as well as log-specific tools like dnum, logshrink, logreducer, and logarchy. We compared the DNSLogzip with 3 popular general-purpose and domain-specific competitors. As shown, DNSLogzip outperforms them all on compression ratio across 3 datasets. It achieves up to 2.3 times improvements over general-purpose twice and up to 3.7 times over domain-specific once. DNSLogzip achieves the fastest compression speed across all datasets. It's up to 2.3 times faster than general-purpose twice and up to 530 times faster than domain-specific twice. Our decompression speed is lower than gzip and LZMA, but still fast enough. We reach around 160 MB per second with a single process, which is practical for real-time applications. The drop in speed is mainly due to extra steps like reordering and restoring addresses, but it's a trade-off worth making. To evaluate how effective each module is, we added them one by one and recorded the results in the table. As you can see, every module improves the compression ratio across all datasets, showing they all help. However, the data transformer boosts compression at the cost of slower decompression, mainly because sorting takes extra time. We tested DNSLogzip with different L values from 10,000 to 55,000, keeping E at 32. Increasing L improves compression ratio, but the gain slows down, and at L equal to 35,000, the ratio dips slightly due to longer line index encoding. We also varies E from 16 to 52 to see its effect. Although a larger base should shorten encoded data, the benefit is offset by reduced Huffman encoding efficiency, so compression ratio stays nearly the same. Compression and decompression speeds also show little change with different E values. To evaluate DNSLogzip performance at the ISPs, we analyze the logs from 2 Tier 1 ISPs over 1 day. To get more detailed insights, we divided the 24-hour logs into 4 times periods, midnight to 6 a.m., 6 a.m. to noon, noon to 6 p.m., and 6 p.m. to midnight. The results show that after compression with DNSLogzip, the logs were reduced to about 31% of their original gzip compressed size for ISP1 and 37% for ISP2, so roughly just 1/3 of the gzip size. To wrap up, DNSLogzip identifies key features in DNS logs, both across lines and within lines. It uses a modular design to enhance and reduce data efficiency. It outperforms both general-purpose and domain-specific compressors. And finally, it cuts storage costs by 2/3 in real ISP environments. Thank you.
Okay, now it works. Okay, thank you for the presentation. Any questions from the audience?
Hi, Marco from Politecnico Torino. Nice talk. One story is storing data, one story is querying data. Have you thought about using some special index or your indexes to speed up the queries to the dataset, or not yet?
Sorry, because I'm not the author of this paper, so you can feel free to send the email to the main author of this paper. Thank you.
Okay, thank you. Thank you, Shenchen. And if you have any questions, please just contact the first author of the paper.